So the last couple days we've mentioned this f double prime thing, and we've talked about what it means, and you guys guessed correctly that it means the derivative of the derivative. So higher derivatives, not only we're going to take second derivatives, we'll take third derivatives, 20th derivatives, whatever. But for example, like it says here, a second derivative is the derivative of the derivative. So the notation that we use is f double prime of x. And that equals, so remember this is our notation for the derivative. D by dx means the derivative with respect to x of, and then normally we put our function in here in the brackets, so we put f prime of x in the brackets. So basically it represents the rate of change of the rate of change. And the example that we very briefly talked about was acceleration. So if you're physics people, you start with position, and then velocity is the rate of change of position, and acceleration is the rate of change of velocity. So it's kind of like the rate of change of the rate of change of position with respect to time, but more about position, velocity, and acceleration in a little bit. So again, we can interpret the second derivative as the rate of change of f prime. All right, so we've got this first example here, talking about Wall Street. So on September 4th, 2003, the Wall Street Journal printed the headline, "Stocks go higher, though the pace of their gains slows." So what does this say about the first and second derivatives? So let's start with a possible graph. I think that might help first before we start looking at the first and the second derivative. So it says stocks go higher. So that to me says that it's increasing. Then it says though the pace of their gains slows. So the stocks are going higher, they're increasing, you've got a positive rate of change the entire time, but they're slowing down. So it's going to look something like this. Something like that. So again, look at the phrase. Hopefully that makes sense to you. Stocks go higher, so they are. I mean, they're increasing, but it says the pace of their gains slows. So down here at the beginning, it's increasing at a much faster rate, and the rate itself is starting to slow down. So what does it say about the first and second derivatives? Well, if it's increasing, we've talked about this before, increasing means that the rate of change is positive. So the first derivative is positive. And that's because our function is increasing. So we don't care at what rate it's increasing for the first derivative. For the first derivative, if our function's increasing, the first derivative is positive. If our function is decreasing, the first derivative is negative. But then looking at the second derivative, when we're talking about f double prime, we want to know how f prime is changing. Well, f prime is positive, but it's actually getting less positive. So it's technically decreasing. So, maybe we have a slope of 2 here, then the slope is like 1, and then 1/2, and then 1/4, and it's headed towards 0. So even though the slopes are positive, the slopes are technically decreasing as they go. So f double prime is actually negative. So in this situation, we would say that this graph is increasing, but at a decreasing rate. And so we've seen things like that actually very briefly in the homework, like increasing at an increasing rate, increasing at a decreasing rate, decreasing at an increasing rate, decreasing at a decreasing rate. So that brings in the second derivative. It's kind of a second aspect of what these functions look like. So our notation, we start with f double prime, which is what we just wrote down, and then we've got f triple prime, which is the third derivative or the derivative of the second derivative. And then after that, it would be ridiculous to continue to write those little tally marks. So after third, you put your derivative in parentheses in the superscript. So that would be the fourth derivative, the fifth derivative, etc. So whatever number you put up there in the parentheses, it's that derivative. Okay, and then the Leibniz notation that we talked about, remember this dy by dx. This is the derivative of y with respect to x. And then the second derivative is d squared y over dx quantity squared. That represents the second derivative of y with respect to x. And then with this notation, let me write a little note about this. This is if we take the derivative with respect to x of the derivative of y with respect to x. And so when you take the derivative of the derivative of y, that's in this notation, it's kind of strange. That's why you get d of dy, so that's where the d squared comes from, and then dx times dx is kind of like dx quantity squared down here. Why they don't have it in parentheses, I don't know, but that's where that notation comes from. So this is the same as this. And then for the third, we have d3y with respect to x, etc. So just to note, when you see this, the exponent is always here in the numerator, but it's always here in the denominator. See there, you've got the third, you could have the fourth, the 20th, whatever you want. So for example 2, we're going to calculate the second and third derivatives of y equals the square root of x. Well, something to point out, which I'm hoping we're aware of, there's no way to get the second derivative without getting the first derivative. So anytime you're asked for multiple derivatives, you have to start with the original derivative, and then we can work our way up from there. So just a quick note, square root of x is x to the 1/2. This way we can apply the power rule that we learned the other day. So the power rule says if you've got x raised to some sort of power, now it can be anything, fraction, decimal, positive, negative, whatever. It doesn't just have to be a whole number or just an integer for this power rule to work. So y prime, this is our first derivative, the power of 1/2 comes out front, and then I subtract 1 from my old power. So 1/2 minus 1 is a negative 1/2. Now normally I would simplify that, put the square root of x in the denominator, but my goal is to get my other derivatives. So next, y double prime, I take the derivative of this, so my negative 1/2 comes out front. It's going to multiply by the 1/2 that was already there. So negative 1/2 times positive 1/2 gives me negative 1/4 x, and then I take the power of negative 1/2 and subtract 1 again. So that's negative 3/2. And again, in just a second, I will clean that up. I want to get the third derivative first. So y triple prime, that's what we call that. Same exact power rule again. We're going to take this 3/2, multiply it out front. It'll multiply by the negative 1/4 that's already there. So I will get a positive 3/8 x, and then my power will drop down by 1 again to negative 5/2. So let's write these again. So this will end up being negative 1 and then over 4x to the 3/2. So I end up with a positive 3/2 down in the denominator. If you wanted to write like the square root of x cubed, that would be fine, but leaving things in powers like that is totally fine too. 3 over 8x to the 5/2 is how we would officially write that third derivative. All right, it is just kind of, there are lots of rules that we kind of ignore in calculus, but negative exponents is something that I like to continue on with. Okay, example 3. This notation, again, in that Leibniz notation, means that you're taking the second derivative. D squared means you're taking the second derivative of this function right here. Again, keep in mind that taking the second derivative, we need to find the first derivative first. This requires a quotient rule from us because we've got a numerator of 1 and then we have a denominator of t cubed plus 1. So let's do some little side notation over here. So remember we've got like high, for high, d, low, all that little cutesy stupid stuff that we did for the quotient rule. So the high, which is the numerator, is 1, which means d high, or the derivative of the numerator, is 0 because 1 is just a constant. Low is the numerator, that's going to be a t cubed plus 1, and then d low, that's the derivative of the denominator. Here I do the power rule on the t cubed, I get 3t squared, and then technically plus 0, which I don't need to write. So for my first derivative, so the derivative of, the function, whatever it is, with respect to t equals, I do low d high, so low times d high, I'm multiplying by 0, so it's just going to end up being 0, minus high d low, well 1 times 3t squared is just a 3t squared, and then all over low, low. So I take t cubed plus 1 and square it. So I end up with a negative 3t squared in the numerator, and then in the denominator, because this is kind of like a composite function, I've got a t cubed plus 1 inside of a squared function. I don't have a rule for that yet. Eventually I will. So what I need to do is I need to FOIL it out. So when I FOIL it out, I'll have t cubed times my imaginary second t cubed. It gives me t to the 6th. Outside, inside, I'll have a t cubed times 1 plus 1 times t cubed. So that gives me a positive 2t cubed. And then for my last, I have plus 1. So that's my first derivative. Okay, so what I need to do the second time is do the entire thing over again. So let's box that up here. just so I can keep everything separate. So round 2, high is the numerator, so that is a negative 3t squared. D high would be the derivative of the numerator, so that 2 comes out front, multiplies by the 3, so I get a negative 6t. Low, of course, is the denominator, which is a beautiful t to the 6th plus 2t cubed plus 1. Just imagine if you were doing this the limit way. And then d low, we're just doing some power rules here. So the derivative of this first piece, 6 comes out front, power drops down to a 5, plus, here the 3 multiplies by the 2, so I get a 6t, and the power drops down to 2, and then of course the derivative of 1 is just 0. So when I put this whole thing together, the second derivative of our function with respect to t equals, so I have low d high, so here's low, and then times d high, which is a negative 6t, and then minus high d low, and then all over, low, low. So this little quantity right here, squared. So lots of things to do up here. So first of all, we're subtracting a negative quantity being distributed. So let's change this to plus a positive, which is totally, totally fine. So let's look at all our terms here. Let's see if we can make this happen all at once. So this term right here, I've got a t squared, t to the 6th times a negative 6t. So here I get a negative 6t to the 7th. And then over here, let's just write it all out. Okay, so here I'm going to distribute a negative 6t to these terms. So I get a negative 6t to the 7th. Here I get a negative 12t to the 4th minus 6t. And then over here I'm going to distribute a 3t squared. So plus 18t to the 7th. That's what I was trying to do, is get those sevenths combined up just in my head. But all right, and then plus last term, here I get an 18t to the 4th all over my denominator. Let's take a quick shortcut there so you can write it out for our last time. Equals, then I've got my sevenths combined, so that is a 12t to the 7th. So I got those. And then I've got the fourths. So combine these two together, I get a positive 6t to the 4th, got those, and then minus 6t. And then all over my denominator, so this thing right here, remember the term in parentheses was eventually this thing, or was once this thing squared. So what I could write is this quantity to the 4th if I really wanted to make it compact. Because remember, in parentheses here, without the squared, that's this. So if I took this and I squared it, I would have t cubed plus 1 to the 4th. So this is the simplest way that I can write that derivative. Okay, fun, very fun. You'll eventually get to the point where these things are nothing. All right, and what will eventually happen with polynomials? So with polynomials, eventually, if you keep taking the derivative, like let's start with like a t to the 5th, or an x to the 5th, I guess. I just have t's on the brain. So x to the 5th, if I take the derivative of x to the 5th, I will get 5, and then x to the 4th, it will drop down. And then if I take the derivative again, the 4 will come out, multiply by the 5, I'll get 20 x cubed. So this is the original function. Here's my first derivative, here's my second derivative. Third derivative, the 3 would come out front, multiply by the 20, I'd get 60. Power would drop down to 2, so that's the third derivative. Then again here, the 2 would come and multiply by the 60. Power would drop down to a 1. And then one more time here, the 1 comes out front, is by 120. Of course, then it's x to the 0, because this is really just a linear piece. So the derivative is just 120. And then the derivative of 120, since it's a constant, is just 0. So now, if we're talking about any polynomial, and not rational functions, no, square roots, nothing like that. Polynomials, remember, are just whole number powers. No fraction powers, decimals, negatives, nothing like that. What will eventually happen with polynomials is you'll eventually take enough derivatives that you'll get 0. So it will eventually go to 0, no matter what polynomial you start with. And again, polynomials are only whole number powers, positive whole number powers, no fractions, nothing like that. It will eventually go to 0. All right, so got some more of this stuff here. So particle motion, this is what we very briefly talked about at the very beginning. If s of t is the position function, then s prime, that represents the derivative, that is, we use v of t, and that is our velocity function. So our velocity function, this is the rate of change. So velocity at time t, that is the rate of change of the position. That's what we were talking about. And then the second derivative, so s double prime, that's the derivative of velocity. So let's write a couple notations here. So v prime of t, we write that that is the acceleration. So the second derivative of position is also the first derivative of velocity. So that's like the rate of change of the rate of change. And there we get acceleration. So this is the acceleration at time t. All right, and then that is the rate of change of velocity. Or the second rate of change, the second derivative of position. All right, so graphical interpretation. We're going to graph x squared So it's your classic x squared function here. Nice normal parabola, goes right through the origin. So something that I want to write down here. Oops, sorry, just trying to get some colored markers so I can point things out. So the derivative of x squared, y prime, just do a quick little power rule, we get 2x. So if I wanted to know the derivative at any point in time, I would just plug it into that 2x. So, say for instance I wanted to know the derivative at 0, I would just plug in x equals 0. That of course gives me a derivative at 0 down to the bottom here. But then let's say I wanted it x equals 1. When x is 1, I plug it in here, I get a derivative of 2. When x is 2, I get a derivative of 4. When x is 3, I get a derivative of 6. If I go back the other way, when x is negative 1, I get a derivative of negative 2. When x is negative 2, the derivative is negative 4. And when x is negative 3, the derivative is negative 6. So you can see the pattern that it's taking. Over on the left-hand side, all of my derivatives are definitely negative because I've got a decreasing half on that side. And then on the right, all my derivatives are definitely positive. Right at the bottom, that's where I'd have a horizontal tangent line. That's a slope of 0. So you get these values just by quickly plugging it into this derivative function. So the graphical interpretation that we're trying to look at, what's very important, what is happening to the rate of change as x gets larger? So as we go from this point over to this point, so look at these values, negative 6, negative 4, negative 2, 0, 2, 4, 6. All of these derivatives are constantly increasing. I start from a negative value and they just constantly go up and they're going to keep going up, 8, 10, 12, 14. So the rate of change as x gets larger, it is increasing. The rate of change is increasing. So what happens is you start with a steep negative slope, you go to a less steep negative slope, it's eventually 0, then you have a less steep positive slope, then you have a more steep positive slope. So that's super important, is that the rate of change itself is increasing. So that means that f prime is increasing. So when we say f prime is increasing, what that means is that the second derivative is positive. Think back to the relationship between f and f prime. If f was increasing, that meant its derivative was positive. So if f prime is increasing, that means its derivative, f double prime, is positive. So say that again. If f was increasing, its derivative, f prime, is positive. So if f prime is increasing, its derivative, f double prime, is positive. So let's look at the exact same thing with negative x squared. So this is, very similar to our other parabola. This one just gets flipped upside down. So y prime is a negative 2x. Again, just a very quick power rule on this function here. The 2 multiplies by the negative that was already there. So if I wanted to plug in any values, if I plugged in 0 in here, I would get a derivative of 0. If I plugged in 1, the derivative would be negative 2. The derivative at at 2 is negative 4. The derivative at 3 is negative 6. If I go off in a negative direction, the derivative at negative 1 ends up being positive 2, because I plug it in here. The derivative at negative 2 is 4, and the derivative at negative 3 is 6. So if we look at all these values, again, hopefully that makes sense just by looking at some of these values, looking at the picture. The farther I go in this direction, I have an even steeper positive slope, because this is increasing through here, then it hits 0, and then the function starts decreasing. So again, what is happening to the rate of change? So these red numbers right here represent the rates, the slopes. They're constantly decreasing. They start at 10, 8, 6, 4, 2, 0, negative 2, negative 4, negative 6, negative 8, negative 10, negative 12, etc. So they're constantly decreasing as we move through this curve. So the rate of change, it is decreasing. And so remember what that means. F prime represents the rate of change. F prime is decreasing. So just like we talked about with the last function, except the opposite, what can you say about the second derivative? Well, if f prime is decreasing, that means its derivative is negative. And the derivative of f prime is f double prime. So that means that f double prime is negative. And so we'll end up talking more about these over the next couple days, but really the thing that we want to look at, because when we talk about the sign of f prime, if f prime is positive, that means the original function was increasing. If f prime is negative, that means the original function was decreasing. When we talk about f double prime, when f double prime is positive, when f double prime is negative, that actually ends up being the shape of the graph. See here how this one kind of bends upwards? Bending upward like this means you have a positive second derivative. Bending downward like this means you have a negative second derivative. But like I said, we've got kind of an entire day where we're going to talk about that. This is just a very brief intro.